Hello everyone, my name is Oluwaseun Martins, and in this session we'll be looking at the computer numerical control machine, which is commonly called the CNC machine. Now, automation is one of the big things that has happened to manufacturing industry, and one of the areas where automation is critically used in manufacturing is the manufacturing of parts, where the CNC machine finds its most use. So in this course, we'll be looking at the CNC machine, their applications, and we'll also be looking at the programming of a CNC machine. So without wasting much time, let's look at our agenda for today. So for the agenda, we have number 1, what is a CNC machine? Number 2, the operational features of CNC machine. Number 3, difference between the NC, CNC, and DNC machine. Number 4, CNC machine programming basics. Number 5, CNC programming with the CNC Simulator Pro software. What is a CNC machine? Now, before the introduction of automation into manufacturing, when a part is to be manufactured, machine tools are controlled manually by machine operators, which means every operation of the machine has to be dictated by the operator, particularly the feed rate, the depth of cut, the speed, and other functions that has to do with the spindle being turned off or turned off, coolant being turned on or turned off, are to be controlled manually by the operator of the machine tool. But with the introduction of automation, particularly the CNC machines, all of these motions, all of these operations, the feed rate, the depth of cut, the speed, are done automatically by the part program. So a CNC machine in itself is a kind of machine tool which the functions and motions of a machine tool are controlled by means of a prepared program containing coded alphanumeric data. So the kind of program which is basically called the part program for CNC machine is coded using alphanumeric data, which means it usually have alphabets and numbers. So that is the part program structure. So there are different types of CNC machines that are used in industries. Some of them are listed here, which are the CNC milling machine, CNC lathe and turning machine, CNC drilling machines, electrical discharge machines, flame and laser cutting machines, water jet profilers, CNC plasma cutting machines. The methods by which the part program can be input into the CNC machine are basically through these 4 means. Number 1 is the manual data input. Number 2 is the program preparation with CAD/CAM systems. Now, there are some CAD/CAM systems that when you create your part on them, you can equally generate the part program directly. So that's another means by which you can get your part program prepared for a CNC machine. Also, programming data from a PC to CNC machine. So you can program your part program, you can write your codes on your computer and send it to your CNC machine. Then also program data transfer from the PC to the DNC operation. Now, the operational features of CNC machine. The diagram here shows the operational features of CNC machine, where you have the input device from where the part program will be sent to the CNC machine. Now, the MCU here, which is machine control unit, is with the CNC machine, and the MCU is divided into 2, which is the data processing unit and the control loop unit. So from the MCU, the motion data goes to the driving system of the CNC machine, and also miscellaneous functions such as coolant on, coolant off, spindle on, spindle off. They also go to the machine tool Now, there's always a feedback system because part programs are for positions and velocity. So the coordinates of the tool and the workpiece has to be monitored. So there's a feedback system that checks the part program instruction against the actual operations on the machine, so which goes back into the MCU, so that necessary adjustment in terms of current or voltage to actually actuate the appropriate position and velocity of the system is sent to the machine tool and driving system accordingly. And also there's always a display unit, so that the operations going on the machine in terms of what line of the part program is being executed by the CNC machine is displayed on the display unit. The elements of a CNC machine. The first element is the part program, which we have talked about repeatedly. Now, the part program is a detailed alphanumeric set of commands to be followed by the machine tool, which consists of positions or motions, machining parameters, and on or off functions. So for every part program, there has to be the position or the motion, then the machining parameters, the feed rate, the spindle speed, maybe you are cutting in mm or in inches. All those are machining parameters, and also the on and off functions, the coolant on or off, a tool change, the spindle on or off. These are on and off functions which are equally captured in the part program. Then the next thing of the element of a CNC machine is the MCU, which is the machine control unit. Like we discussed earlier, the MCU is with the machine tool itself, and it is divided into two, which is the DPU and the CLU. Now, the MCU is the microcomputer that stores the program and executes the commands into actions by the machine tool. The DPU in itself, what the DPU does is to convert the part program into a usable format for the MCU and interpolation algorithm. Now, what the DPU does is to convert the part program that the user or the operator, in this case of the machine tool, has already written. To do that for the DPU consists of a control system software, calculation algorithm, translation software that convert the part program into the usable format, and also there are interpolation software to achieve the smooth motion of the cutter and for editing of the programs. So the DPU is a whole lot, because without the DPU there is no way the CLU would function. And for the DPU to function properly, it consists of the control software, the calculation algorithm, because there is a lot of calculations that the machine will do based on the part program, and also translation software, so that I can convert the part program into the format that will be understood by the MCU. And also interpolation algorithms. Interpolation is how the tool interact with the workpiece. So the DPU equally has the interpolation algorithm to achieve the smooth motion of the cutter, and also to edit the part program in case there is any need for a change due to probably an error. The CLU, on the other hand, what the CLU does is to control the actual motion that is actually being seen on the machine tool. So every motion of drive, of tables, of probably a lead screw or whatever it is that is physical to see is being done by the operation of the CLU, which is the other half of the MCU. So the CLU operates the drives attached to the machine lead screw and receive feedback signals on the actual position and velocity of each one of the axes. So the CLU is responsible for the actual movement of every component or every drive on the machine 2, and also the feedback in terms of the actual position and velocity of each of the coordinates is received by the CLU, which in turn reports to the DPU, and whatever adjustment in terms of voltage and current to ensure that the appropriate position or coordinate is attained is sent back to the CLU. So machine 2 could be a lathe, could be a milling machine, could be a laser or a plasma cutting machine. So for every machine 2, there are 3 linear axes, which is the X, the Y, and the Z axis, and there are 3 rotational axes, which is the I, the J, the K, and also there's the tilt, depending on the dexterity of such a machine 2. So a combination of any of this will make the possible interpolation or the possible axis that can be attained by such a machine 2. So it could be 3 linear, 2 rotational, and the tilt, or it could just be linear and rotational axis alone, or probably a combination of the both, depending on the level of the sophistication of such a machine. Now, the category of a machine 2, depending on the structure of the controller unit, which is the MCU now, a machine 2 could be a numerical control, which is NC, could be a computer numerical control, CNC, or could be a DNC, which is a distributed numerical control machine, depending on the structure of the controller unit. Now, the controller unit of a CNC machine, or the machine 2 in this case, is the MCU. So depending on the structure of the MCU, the machine can be said to be an NC, a CNC, or a DNC machine. Now, what makes a machine an NC machine? Now, for an NC machine, the MCU, which is the machine control unit, is a tape reader. So whenever a new part is to be machined, or whenever a new program is to be run on such a machine, the punch tape must be read. So for an NC machine, the MCU is a tape reader, and the way by which it actually reads its program, the part program in this case, is to read the punch tape. But for a CNC machine has the onboard computer, which implies that with a machine 2 that is a CNC machine, there's always an onboard PC on such a machine, which has its own ROM, that has a random read-only memory, and the display screen for the machine 2. So in that case of a CNC machine, since the machine itself has its own PC, the controller unit on it is a PC, the program can be written on the machine, the program can be copied from the machine, the program can be transferred to the machine. Now, the only drawback with a CNC machine is that there is no feedback, in the sense that, fine, the machine in itself is a closed loop, but whatever work is being done on the machine, if the operator is not in proximity of the machine, if there's any problem on the machine, the operator cannot tell, so it cannot be operated remotely. And that's where the DNC machine comes in. With the DNC machines is a network of CNC machine, where you have at least two CNC machines, which is being controlled by a personal computer, and that personal computer receives feedback from the CNC machines. So the operator can be with the personal computer, which will be in another location, and every operation on the CNC machine can be seen on the personal computer by the operator, and whatever part program is to be done on any of the CNC machines can be sent from that personal computer to the CNC machines, and the operator can know firsthand the the conditions of the machine in terms of their work rate, in terms of the scrap rate, in terms of the working process, in terms of production rate and all of that, which is not possible with just a CNC machine. So the difference between the DNC and the CNC is that the CNC machine does not have a feedback, whereas the DNC machine has a feedback, and the DNC is just a network of CNC machines. So that is the difference between the three. And here is just showing the graphical illustration of the NC machine, where the MC is a tape reader, and this is the punch tape where the program of instructions will be, so that the punch tape will have to read the tape reader, which is the MC. You will have to read the punch tape to actually operate the machine. For the CNC machine, it's an onboard computer. The MC is an onboard computer, and the program is actually written probably externally or written on the onboard computer itself. It can be copied from the onboard computer. It can be copied to the onboard computer to operate the CNC machine. So the DNC machine is where you have a network of CNC machine with a central computer, whereby they are connected via a communication network. So the operator can be with the central computer, and from there it can determine and know the operations of the connected CNC machines on the network. So for the CNC machine programming basics, number one is the type of programming mode on the CNC machine, and there are two programming modes on the CNC machine, which is the incremental or the absolute. Now, neither of this programming mode is right or wrong, but it depends on your preference as the operator. In this case, you can decide to program in incremental or program in absolute. However, if a program has been started as incremental, there is no means of changing to absolute within the same program, and the opposite is equally true. Once you start with absolute programming mode, you cannot in between the same program switch to incremental. Now, what is the difference between the two? For incremental programming modes, the part programming code is the G91. We talked about the part program being an alphanumeric data. So the G is the alphabet and 91 is the number. So once the part program reads G91, the machine knows that the programming is in incremental. Now, what does it mean to program in incremental? What it means is, for every point of operation on the part on that machine, there is no common reference point. There is no common origin of measurements of every point of operation, of every coordinate of operation on that workpiece. So, for instance, if you look at this diagram, the hole here, 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 they are measured from the previous hole. So this hole here, the center of this hole is measured from this edge, which is 0.250 mm, and the center of this hole here is measured from the center of this, which is 0.75. The center of this is measured from the center of this, which is 0.75. The center of this is measured from the center of this, which is 0.75 as well, and so on. So the current coordinate of operation, its origin is measured from the previous coordinate of operations. That is the incremental. So there's no common origin. However, you measure the origin of the current point of operation from the previous point of operation. That is for incremental. For absolute, the programming code for the absolute is the G90. So once the machine sees, once the part program reads G90, the machine knows that the programming is in absolute. For the absolute, there is a common origin in this case. So every point of operation is measured from the common origin. So point 1 is measured from here. If this point is taken as the origin, point 2 will equally be measured from here. Point 3 we measured from here. Point 4 we measured from here. Point 5 is equally measured from this point. So depending on conveniency, one can decide to program in incremental or absolute, depending on the convenience. Now the next point under the CNC programming basics is the CNC programming categories. Now there are two categories as well for the CNC programming category: the point-to-point system and the continuous part system. The point-to-point system. In the case of point-to-point system, the coordinate of operations on the workpiece are at different points, which specifies different coordinates in the x and y axis. So here we have point 1, point 2, point 3, and point 4. So the coordinate of point 4 is some value in y here and some value on x-axis here. Also for 3, some value of x here and some other value of y here. So the tool on the machine tool has to move from one coordinate to the next, from point 2 to the next, which is point 3, from point 3 to the next, which is point 4. So in this case, it's similar to where you are working on a drilling machine or a milling machine, whereby you need to mill a hole or drill a hole or mill a particular profile at different coordinates on the workpiece. So in this case, the tool is not in constant contact with the workpiece as it moves from one coordinate to the other. So for point to point, the tool is not in constant contact with the workpiece as it moves from one coordinate to the other. That is the point to point. Now, point to point will apply to machine tools other than the lathe, because for the lathe, the tool has to always be in constant contact with the workpiece as it travels from one coordinate to the other. So for the continuous part system of programming category, the tool is always in constant contact with the workpiece as it moves from one coordinate to the other, as you can see in the two parts of this two parts that we show here. So this is the tool. The tool will go continuously in contact with the workpiece as it moves from one point to the other. And also here is the same. So it continues to be in contact with the workpiece as it travels from one coordinate to the other. So that's the difference between the point to point and the continuous part system for the tool movement. So for interpolation is the method by which a contouring machine tool moves from one program point to the next. So for every coordinate in the part program, how the tool will move from one coordinate to the next, it's what is called interpolation. So interpolation could be linear, could be circular, could be helical, could be parabolic, and could be cubic, depending on the dexterity possible with such a machine tool. So for linear, the interpolation from the previous coordinate to the next is a straight line, whereby for circular it is either probably clockwise or counterclockwise for helical and all of that. So for linear interpolation, the part program code is the G01. So once the part program reads G01 on a particular line on the part program, the machine knows that whatever coordinate that is coming after G01 means that the tool will transit or interpolate from the previous to the next via a straight line. And the common interpolation with machine tools is the linear and circular. only for very sophisticated machine tools has the helical, the parabolic, and the cubic, which are particularly used to manufacture parts such as that of the automobile part or the aerospace parts. So for the common MCUs, they can handle the linear and the circular interpolation. Now for the circular interpolation, so we'll be looking at the linear and circular interpolation in this course. So for the circular interpolation can be clockwise or counterclockwise. So for clockwise interpolation, the part program code is the G02, and for the counterclockwise, the part program is the G03. So once the part program on a particular line reads G02, the machine knows that the interpolation from one coordinate to the next is clockwise interpolation, and when it reads G03, the machine knows that it's a counterclockwise interpolation. And next thing is the canned cycle. So the canned cycles are standard subroutines or procedures that are already stored in the library of the machine tool. So they are pre-written. So that's why they are called canned, and because they are run in a cyclic manner, so it's a cycle. Now, what is the benefit of canned cycles? For any part to generate the part program would run into series of lines of part program codes. To minimize that, one of the ways to minimize the lines of codes that you might have on your part program is to use the canned cycle. A canned cycle can reduce your line of code by as much as 10, 20, 50 lines on your part program. So part program can be well detailed using a canned cycle. So one canned cycle can take care of so many lines of part programs, and a lot of them are possible on the MCUs of machine tools. However, there are two types of canned cycles: the fixed and the variable type of canned cycle. So for the fixed, it implies that the subroutine are not adaptable to a specific user need. So which means these are canned cycles that are to be used the way they are. For the fixed, they cannot be adjusted, they cannot be edited, where the variable are the ones that can be adapted to the user's specification. So those are the two types of canned cycles that you might have. So there are so many canned cycles. We should be looking at some of them in this course when we get to the simulation, so that we can get to understand them in proper terms. Now, another basics of programming is the kata programming, particularly for milling operations. Now, for every part program, every coordinate that is being quoted on a part program, what the machine tool wants to do is to ensure that the center of the tool coincides with that coordinate. And here is where the problem is. If the coordinate must always coincide with the center of the tool, which implies whatever profile that is being required will be less than the radius of the cutting tool, because the cutting tool itself has its diameter. Looking at a milling CNC machine now, every cutter on the milling CNC machine has its own diameter. So, and if the machine must always coincide the center of the milling machine tool with the coordinate that is being coded on the part program, the profile on the workpiece will always be less the radius of the cutter. So to avoid that, there are two methods. Number one is the cutter center programming, or programming the tool, and the other one is the zero radius programming, or programming the part. So for cutter center programming, what the operator will do in this case is that whatever coordinate that is to be quoted in the part program, the operator would add the radius of the tool to that profile so that the cutter can stay its own radius away from the required profile. However, this is only applicable whereby the operation on the workpiece will only be achieved by just one cutter. Where there will be a lot of cutters that will be used on a workpiece before the final profile is obtained, adding the radius of every cutter which will be used to the profile will be very difficult. So that is where the zero radius programming, or the programming the part, comes in, which is the G41, G42 and the G40. Now this is what is called the cutter compensation. So the G41 is cutter compensation left, G42 is cutter compensation right, and the G40 is cutter compensation cancel. How to use G41 or G42 is to observe to determine what side of the workpiece is the tool. If you look at this diagram, you see that the tool is to the left. Observing from the rear of the tool is to the left of the workpiece. So that is why it's cutter compensation left, which is the G41. And in this other diagram, looking from this angle, the tool is to the right of the workpiece. So that is why it's G42, which is cutter compensation right. Now to cancel the cutter compensation, the G40 code is being used. So that is the explanation of the G41 and G42. Then another very critical issue again is the tool offset. That is the tool length compensation, which is the G43, G44 and the G49. So G43 is the tool length compensation positive, G44 tool length compensation negative, then G49 tool length compensation cancel. Now looking at a milling machine to understand the concept again, machine tools can have series of tools in the tool chamber, and so many tools might be required to machine a particular profile on a certain workpiece. So before the beginning of the operation, what the operator will do is to use a particular tool to serve as the datum tool. So the tool will be on the spindle, and the operator will try to lower the spindle until the tool touches the surface of the workpiece. So once the tool touches the surface of the workpiece, the operator will use the MCU to measure that coordinate, that z-axis, because the cutting axis is the z-axis for all the machine tools. So for the milling or the drilling machine, so the approach of the workpiece, which is in this direction coming down to the workpiece, is the z-axis for the probably your drilling machine tool or the milling machine tool. So after the operator tries to touch the surface slightly of the workpiece with the datum tool, in this case, the operator will use the MCU to measure that z-axis, and that z-axis will be set at 0. So that becomes the datum. That tool now becomes the reference tool. Now you agree with me that if a longer tool is changed on the spindle and the operator tries to touch that same surface, the tool will not go as further down as the initial tool, saying that if the datum tool is shorter than the next tool that is being used, to touch the surface with the longer tool now, the z-axis will not go as low as the datum tool. So in that case, the cutter compensation, the tool length compensation, will be a positive tool length compensation, which will be the G43, which means, because for z-axis going into the workpiece is negative Z, and going away from the workpiece is always positive Z. So because the datum tool has been used to set the 0 point, so putting in a longer tool now, which will not make the Z-axis to go as further down as the datum tool, will be a positive tool length compensation. And putting in a shorter tool than the datum tool will cause the spindle to go further down than the datum tool, which will result into a negative tool length compensation. So that is the G43 and G44. And the G49 is to cancel the compensation. So, and one thing is to be very noted here, the tool length compensation or the contact compensation, whenever they are being used and they are no longer to be used in the same parts program, they must be cancelled, else the tool will begin to misbehave. So once you are done using a compensation, it has to be cancelled before any other line of code should be written. So that's another very important point to note. So from this point, we'll be switching over to the CNC Simulator Pro so that we can simulate and see how the parts program operates for the lathe and the milling machine, so that we can get a better understanding of the parts program. CNC lathe, and we talked about CNC having the MCU as an onboard PC. So this is the onboard PC in this case for this particular CNC machine. So here you have the headstock. This is the headstock of the CNC lathe, and this crosshair that we can see here is the origin coordinates, where you have your X0, Z0 and Y0 for this lathe. However, you don't have Y coordinates for your lathe. It's only the X and the Z axis. I already said that the Z axis is the cutting axis or the tool axis on your CNC machines, while the X axis on the lathe is the workpiece diameter. On the lathe, your X axis is the workpiece diameter, while your Z axis is the tool axis. So you can decide to change this this machine into the milling by just clicking here where you have machines. So I'm just going to change to the milling machine now. So for the milling, this is the milling center. So also the milling also is a CNC milling, and why is that? Is because it has the onboard PC, which is this, also attached to the machine. So this is the MCU in this case. So also this is the table, and see this is the table on your milling, and this crosshair that we can see here on the table here is the origin. That's the X0, Y0 and Z0 for your milling. Your milling is a 3D machine, so it has the X, the Y and the Z axis. Also the Z axis is the tool axis. So, and for the milling or your drilling, you always notice that the tool, I'm not changing the machine yet, you always notice that the tool is always on the spindle. So this is the spindle in this case. So the tool will come downward, or it can retract upward or downward into the workpiece or away from the workpiece. So the Z coordinate for your milling or a drilling machine is the up and down movement of the tool from the spindle. And this is the table, and like I said, this is the origin, where you have your X0, Y0 and Z0 for your milling machine. So let me just change this machine back to the lathe before we take a tour of the CNC Simulator Pro, so that we can get to understand how this part program is being done. For the CNC Simulator Pro, you have the luxury of creating your own tool, creating your own part. So from the settings here, let me just do that again. From the settings here, you can go to the inventory browser using F2. So from the inventory browser, you can see the tools, the mill workpieces, the lathe workpieces, and also materials that are being used to make these workpieces. So for the tools, for the embedded tools for the milling, you have 68 tools, while for the embedded tools for the lathe, there are 37 tools. So all the tools have their details. So if you click here, this is the tool 1, is a left hand roughing external with a nose radius of 0.8. So the next tool is the left hand finishing external. So because CNC machine can take a lot of tools, and that is why the tool change is one of the part code that's on the CNC machine. So you can always switch from one tool to the other depending on the requirements as the profile which is to be done on the workpiece demands. So also you can do that for the mill. So there are 68 tools in the mill tool registry. So here again you have the diameter, you have the tool length, and also you have the tool name, which is an end mill, millimeters. So you can always look at all the tools that you have by just clicking and checking all of those. So depending on the profile you want to create, you might need to go to the tool registry to see which tool can actually get such a job done. And also you can look at the materials. So the mill materials here is the one you have two. These ones were actually created by me. You can also create your own by just clicking hard part. So you can hard part and put in whatever part name, probably part 3 now, because I already created 2 parts already. So this part 3. So what is the x-axis? What's the length on the x-axis? Let me say maybe it's 50. The length on the y-axis, let me say that is 70. So what is the height of the workpiece? That's the z-axis of the workpiece. So let me say that is 5 mm. So you can see that has been created. So this is the new workpiece, which is labeled part 3. So by clicking OK, that has already been saved in the register of the CNC Simulator Pro. So to actually carry out a work on the CNC Simulator Pro, you need to first of all choose the appropriate machine, maybe a lathe or milling. Then you need to know the profile you want to create from the rough stock that you have. So for instance, let's look at this diagram here. So this is the rough stock. The length of the workpiece here is 51.50 mm, and the diameter is 45. And we are requested to create this. So doing a step turn of this diameters, which is 25 by length of 20, and also 35 by length of 20. So this is 25, 35, and this is 45. And the internal diameter here is 12. So this is how the the question always comes. So you have your rough stock and you have your finished profile. So you need to write the part program that would create this profile from this rough stock. So let me just open so here is the part program. We talked about the part program being an alphanumeric coded programming stuff. So the part that has this profile is the part that is added as part in the register of the CNC Simulator Pro as part 1. What I mean here is, if we go to the inventory browser, to the late materials, so part 1 has the diameter of 45 and a length of 75. There are no internal diameters, so it's a solid shaft. So that is part 1. So with this syntax, your $sign add reg part, then the part number is part 1. So what we have here in these brackets is just to put a comment so that whoever is looking at this program will know the diameter and the length of the part 1 that has been added here. Now you notice something, that what we have here is a length of 51.50, and here we are having a length of 75. Why that is so is because the headstock, the choke of the headstock of the lathe would hold a certain length of the rough stock, which will be inaccessible for the tool. So that is why there is an additional length to the rough stock here. Now for this CNC Simulator Pro, the length that is being held by the headstock, I mean the choke of the headstock of the lathe for this CNC Simulator Pro is 22.5 mm. So if you take out 75 minus 22.5, then you have 52.5. So that is the length that will be accessible for the tool, because 22.5 mm would have been held by the choke, which would not be accessible for the tool. So the first thing one needs to do is to set the origin. When you're starting your part program, you need to set the origin, because here, if you look at the headstock here, this crosshair is the origin for this lathe. So this is at the tip of the choke of the headstock is where X and Z is 0. Now at the time the workpiece is being introduced into the choke of the headstock, this origin will fall behind the workpiece, so we need to move it, you know, towards the surface of the workpiece to make that our reference point. And to do that, to transfer this origin coordinate from this point to any point on the workpiece at all, the G code is the G92. So to set the 0 offset is G92. Then you need to specify the X coordinate and the Z coordinate. Now what has been done here is to put in G92 X0, meaning that this cursor will be at the center of the workpiece, because X0 is where the diameter of the workpiece is 0, and that will be the center of the shaft, because lathes only deal with shaft workpiece that are cylindrical. So X0 makes it at the center, because x-axis of the lathe is the diameter of the workpiece. So putting in that X0 means that this origin will be at the center of the workpiece. Now for Z-axis, the Z-axis in this case, going into the headstock of the lathe machine in this direction, in this direction would be to the negative side of Z, and going to the right side of the screen will be the positive direction of Z. So, and having subtracted the length of the workpiece that will be held by the choke of the headstock, which is 22.5, and we are left with 52.25. So it is instructive to just put the Z axis for the G92 on 52.5, so that the origin will be at the surface of the workpiece. So that's what this line is doing. G92 is the 0 offset, and you need to put in the Z and X axis, and x here is 0 because we want the origin to be at the center of the workpiece, and the z is the maximum length of the workpiece, having subtracted the length that will be held by the headstock, by the choke of the headstock on the workpiece, which is 22.5 in this case. So 75 minus 22.5 will give us 52.5. So this line of code will make this origin to be at the surface of the workpiece. So the next thing is to inform the machine that in what programming mode, is it incremental or absolute. Now absolute is G90 while incremental is G91, and in this case the part program here is written in absolute, meaning that there's only one origin for every coordinate that will be taken as the program continues. So which implies this point here is the origin for all the coordinates that will be taken hereafter. So that's absolute. Then G21 is to specify that all the dimensions are in mm, so we are only working with millimeter, while G95 is the feed rate, the feed revolution mode. So G95 is doing that. So that is what this line here is doing. Now the next thing is to start the spindle, and the alphabet is the S, and the RPM is 1000. So spindle starts with an RPM of 1000. That means the headstock will start to turn at an RPM of 1000. That is what that is saying. Now the headstock can turn clockwise or anti-clockwise. So the next thing is to specify, is it to turn clockwise or anti-clockwise. So M03 is spindle start clockwise, while M04, if I change this to 4, will be spindle start counterclockwise, but I'm using clockwise in this case. Then the coolant on is M08. So once the spindle starts and it starts clockwise, then the coolant should be set on. So that's M08. Now the next thing is to put in the appropriate tool. In this case, since what is to be done is an external step turning, in this case what is required is to ensure that a step turning tool is put on the machine. Now T1 is the embedded tool in slot 1 of the tool registry, while M06 is the tool change. Now why this is important is that it's possible for another tool to be on the machine at the point this job is to start. So what this line will do is to ensure that the tool on the machine is changed to tool 1. Now let's see the details of this tool 1 from the tool registry. So we can see here that for the tools, for the late tools, the tool number 1 is the left hand roughing external with a nose radius of 0.8. So it's an external roughing tool. So that is tool 1. So what this line will do is to change the tool to this external tool 1. Then G00 is a rapid transverse without cutting. So you're just telling the machine that I want to move the tool a particular coordinate without cutting. So that's the G00. Now to what coordinate are you moving the tool? So you have to specify the X and the Z coordinates. So here the coordinate that is being specified here is X48 and Z2. Now if you recall that with this line we have set X0 Z52.5 as the origin, which is the surface of the workpiece. So coming here with a rapid transverse without cutting G00, X48 will make the tool to go beyond the diameter of the workpiece, because the diameter of the workpiece is 45 and we are taking X to 48. So the tool will go above the diameter of the workpiece, and also Z2 will make the tool go away from the surface of the workpiece, because the surface of the workpiece has been set to 0 from here. So putting Z2 will make the tool go to the right of the screen, which is away from the workpiece. Now M21 is just a tool, a door close command, which means the door of the machine will be closed just for safety. This door will be closed for safety reasons. So that's what M21 is doing. Now G42 is the cutter radius compensation. If you notice that the tool that we picked has a nose radius of 0.8, this radius of 0.8, so that is why the cutter compensation for the radius has been introduced in this case. Then, since we are doing a step turn, what has been used here is the G71 and G70 roughing and finishing cycle. You know, we talked about cant cycle. So one of the cant cycle that is commonly used in lathe operations is the G71 and G70, which is the roughing and finishing cycle. So let me just explain what this cant cycle does. Now the G71 has two blocks. This is the first block of G71 and this is the second block, and this is the G70 block here. So let me explain the G71 and the G71 first and second block. So for the G71 first block, you have the U and the R. So the U is the alphabet, while whatever number that is coming after it is the depth of cut for every cut in the cycle. So what is being said here is that in this G71 roughing cycle, the depth of cut is 2 mm each time, while the R3, which R stands for the tool retract, and 3 is the millimeter by which the tool will stay away from the workpiece each time it takes a cut of 2 mm. So the first line is just used to specify the depth of cut and the clearance that the tool will give the workpiece after each cut. So G71 U2, which means 2 mm at each cut, and after each cut you stay away by 3 mm. The tool will stay away by 3 mm. Now the second block of the G71, you have the P, the Q, the U, the W. Now what the P and Q here is doing is to specify which line number on this part program code is this G71 going to be active. And here I specify P20, which means this G71, this cutting and retraction of U2 and R3 will start on line N20, that's P20, and will end on line N70, which is Q70 in the G71 code. So which means the cutting of 2 mm and retraction of 3 mm will only be effective on N20, from N20 to N70. So this U2 R3 will only be effective from N20 to R70. So every line that falls from N20 to N70 is where this U2 and R3 will be effective. Now the U1 and the W1 here is the allowance that is being left on the diameter, which is U1. So which means after all the cut has been taken, there will still be left 1 mm on the diameter, and also for the clearance on Z-axis, that's the 1 mm for W. So that is what this tool U and W on the second block of the N71 is doing. The clearance on X-axis, that is the diameter that will be left on the X-axis, in this case is 1 mm, and for the clearance for the Z-axis is 1 mm. Now the block itself starts from N20, which is specified by P20 in the second block, and ends on N70. which is specified by Q70 in the G71 second block. So what is to be done here? N70 X20. So what will happen is that the tool will come to the diameter of the workpiece will be taken down from X48 here to X20. Now there's a G01 here. G01 is linear interpolation, which implies that you want to cut linearly. You're telling the machine that the movement of the tool from one coordinate to the other is in a straight line. So from a diameter of 48, X48, to a diameter of 20, it will go to have a linear interpolation cut on a straight line to a length of 20, Z minus 20, because Z axis is the tool axis. So once the tool is moving toward the headstock is negative Z, and away from the headstock is positive Z. And because the surface of the workpiece has been set to 0 with G92 here, so moving into the workpiece towards the headstock will be negative value for Z. So that means the length of 20 mm diameter will be 20 on the workpiece. That is what this line of code is doing within the G71. So that means from 78 to 20 mm, it will be taking 2 mm at each cut and retract the 2 by 3 mm to get to 20 mm from 48 mm to 20 mm. That will be the procedure. So the next step is to step to 35, a diameter of 35, and the length of that diameter on the workpiece is Z minus 40. So which means at the end of the day, the profile for the step turn will be 20 mm diameter and 35 mm diameter with a step distance of 20 mm in the Z-axis direction. So the final block of the G71 and G70, which is the G70 block, has only one line, which is the P20 and the Q50. So for the G70, it's only going to repeat, you only have to repeat the P and Q number in the second block of the G71 on the G70. So it's the same P20, Q20 that has to be repeated on the G70 count cycle block. Now what is going to be happening in this G70 is the allowance that is left on the x-axis, which is this U1. So what will happen is 1 mm will be the depth of cut on the G70 line, which we have here. This 1 mm that is left on the x-axis on the second block of G71 is what will be taken out on the G70 line. Now G28 is just for the tool to go to a safe position away from the workpiece, and G40 is to cancel the cutter radius compensation, which is the G42 that has been used there. So it has to be cancelled, which is being cancelled with the G40 here. Now again, there's another tool change here to T17. The tool change command is M06. Now let's look at the tool of 217. So T17 is a drill of 10 mm, and the diameter of the drill is equally 10 mm, and the tip angle is 120, and the tool length is 50. So after the step turn has been done, the tool change will change the tool from the roughing tool to a drill of 10 mm diameter, and this G00 again is to be used to move the tool to a particular coordinate without cutting, and the coordinate here is X0, Z0. Because now I want to drill at the center of the workpiece, I need to center the tool to the center of the workpiece, which is X0 and Z0 coordinate. and the length at which the drill will go into the workpiece is Z minus 20 into the workpiece. And to do that, there has to be a rapid transverse linear interpolation command, which is the G01, because G00 is not a cutting transverse, but G01 is a linear interpolation, which means we want to cut linearly, and the drill will go into the workpiece linearly. So that is why the G01 is being used here to specify the next coordinate for the tool, which is Z minus 20. So the drill will go into the workpiece with a length of minus 20. So the next thing that is being done here is to just take the tool away from the workpiece, Z2 with G00, so just a rapid transfer without cutting. Then G28 is just to take the tool to a safe position. Now M09 is to put the coolant off, which we put up with the M8. So M9 is to put the coolant off, while M5 is to stop the spindle, and M20 is to open the machine door, while M02 is to end the program. So if we run the program now, we'll see how the system would execute the work. Now we can see that the workpiece has been hardened in this case, and we can equally see that the door has been closed, and we can see the center now has been changed to this point. So the step turning is being done gradually. That's the M7, that's G70 line, that's the final cut, and the tool has been changed. So that's the final cut. So the tool has been changed into the drill now, and that has gone in by Z minus 20. So you can see the profile now. So this is the 20 mm diameter, this is the 35 mm diameter. So this is 20 mm diameter by a length of 20, which is here, 20 mm diameter by a length of 20, which is this one, and also 35 mm by a length of 20. This is the 35 mm by a length of 20. Now, so this is 20, 20, that makes 40 altogether. So you only have 35 on 20 mm and 20 on 20 mm length. Now this surface will remain as 45 because there was nothing done on this surface. It's only this part and this part. Now the drill has gone in also by 20 mm. So that is the drill, and you can see that the zero coordinate is on the surface of the workpiece, which was done using the G92 here. So let's just run the program again just to have another look at it. So we can see it's just doing the work again. Just zoom it in so that we get to see a close view. So that's the twitching, that's the drill coming in now. And that is that. So let's look at another. So here is another part program code. Now in this case, the part in the part registry is part 3. So let's just look at what the part looks like in the registry. So late workpieces number 3. So this is part number 3. So the outer diameter is 80 mm, the length is 150 mm, and the internal diameter is 50. So what is being requested here? Let's take a look. So here, this is the rough stock. So 126.5 mm the length. So the internal diameter is 50 and the external diameter is 80. And the profile that is being requested is this, to have this stepped on and to bore the internal diameter from 50 here to 70 or 60 thereabout, which will confirm in the program. So these are the diameters: 60 internal, 65, 70, 75, and 80. So 80 here, 75, 70, then 65 here, and the internal is 60 mm, while the other diameter is remains as 50. So 60 mm to bore the internal diameter from 50 to 60 with a length of 30, while the external diameter is to be stepped on to 70, 75, sorry, to 65, 70, 75, while this length remains as 80. So that is the requirement. So here again, just like we did the other time, this is the length of the workpiece based on the length that will be held into the top of the headstock. So 150 minus 22.5, which will give us 127.5 in this case. So if we say 150 minus 22.5, so 127.5. So the G72 here again is being used to set the zero offset, to take the origin of the machine from the tip of the headstock to the surface of the workpiece, just like we did in the previous example. So x0 to the center of the workpiece, x0, and the z-axis is the length of the workpiece, so it takes it to the surface of the workpiece. Now G90 is absolute again. G21 we are cutting in mm. We are using mm, the dimension is mm that we are using. Then the feed per rev mode is G95. Spindle start 1000 rpm, clockwise M3, coolant on M8. T1 is the first tool that is to be used, and M06 is to change to that T1. So G00, move the tool without cutting to X88 and Z2. So move the tool without cutting to this coordinate. Then also the M21 is to close the door of the machine. Let me just remove this end of block from here. So the end of block can come here. So G42, quarter radius compensation. Then G71 again, because we are doing a step turn from a diameter of 80 down to 60, down to 65 to 70 to 75. The internal is 60. So we are using the roughing and finishing cycle again. The first block to specify the cutting and the retraction of the tool in the G71, which I'm taking 1 mm per cut and retracting by 5. You can specify any retraction distance, and can specify any feed rate, any cutting depth per cut, depending on you. Then the second block of the G71, as we explained, has the P, the Q, the U, and the W alphabets. The P and Q are the start and finishing block of the G71, while the U1 on the second block of the G71 only specifies the allowance that is left on the x-axis, while the W specifies the allowance that is left on the z-axis. Now, the line at which this G71 is active is to be specified with the N number, that's N20 to N70.
So this G71, this first block of G71 will only be effective from N20 to N70. It could be any number. Just for instance, if I change this to 80 and this to, sorry, let me remove this, to 80 and this to 120. So I only come here to change this to N80 and here to 120 and here also 80 and here also 120. So the first thing that will happen is x88, that's the tool coordinate on x-axis, which is the diameter of the workpiece, to take it down from there to x65, sorry, using the G01, which is the linear interpolation, and the length of that will be minus 40 because it's going into the workpiece now. It's minus z-axis, is negative in the negative direction of the z-axis, so that will be a length of 40 on the workpiece to a diameter of 65. Then the next thing here is x70 again, because the diameter is to be stepped in 65, 70 and 75. So the next diameter after 65 is 70, and 70 by a length of minus 80, and also 75 is next diameter by a length of minus 115. Now if you look at the diagram here, it's been specified as 40, 40, 35, but when you add 40, 40 will give 80, and 40, 40, 35, that will give 115. So that is where all this length came from. So the final clearance that is left on the x-axis on the second block of the G71 is being taken by the G70 block here, and in the G70 you only specify the P and Q number of the second block of the G71. So this allowance that is left on the x-axis is taken out with this G71 here. Then G28 is just to take the tool to a convenient position away from the workpiece. G40 is to cancel the quarter compensation, and here again the tool has been changed to T11. So let's look at what tool is T11. So it's an internal roughing, so we want to actually bore the diameter further. So T11 is an internal boring tool. So also we are using the G00 to take the workpiece, the tool to this coordinate x40 z0, internal in this case. Z0 is just the surface of the workpiece because we have set that surface of the workpiece as the 0 coordinate for the z-axis. Then equally using the G71 again. So here is U2, R2, P80, Q90. So this is N80, N90 in this case. We can equally change this to maybe 200 to 210. So I will equally change this one to 200 and this one to 210, and also change the G70 line to 200 and 210 in this case. So what will happen here is the internal boring using the G71 and G70 also. So taking 2 mm per cut and retracting by 2 mm, and also leaving an allowance of 1 on x-axis to be cleared out by the G70 block, and an allowance of 1 mm for the z-axis. So to take it from x40 to x60 with a rapid transverse with the linear interpolation of minus 30. So that is what is happening here. So this depth of 30 for the 60 mm to bore this diameter inward 60 mm from 50. So that is what is happening on this line. So diameter should go to 60, the depth of minus 30 using the linear interpolation. and here is the G70 block, which will take the allowance of U1, which is 1 mm on the x-axis, and after that rapid transverse without cutting G00 to take the tool to the home position, which is X0 Z2, and G28 is to take the tool away from the workpiece. M09 is to put the coolant off, M05 to stop the spindle, M20 is open the door, then M2 is to end the program. So let's run the program and let's see how the code. So the first thing to be added is the workpiece. This is the workpiece. The workpiece has been added. You can see the internal diameter of 50, external, and all of that. So the step turn will be done initially, then after the boring will be done. So the first G71, G70 roughing and finishing cycle is what is being executed now. So the machine is on this line. So the finishing cycle for the G70 is what is being done now, and after that the tool would be changed to the internal roughing tool. Now the internal roughing tool has been changed, and the internal diameter is being done now to a length of 30 mm. So that's the finishing cycle for the internal boring. So M20 to open the door and M2 to end the program. So if you look at it, we can see here that the internal diameter has been further increased to 60 from 50. This is 50, this is 60, and also the step turn for external has been done to 65, 70, and 75 here. So that is what has been done in this case. So let's see another. So here is the part program for another illustration of the late part program. Here the part 2. Let's look at the part 2 here. Just going to the inventory, we can look at what the part 2 looks like. So the late work pieces. So here is this is the part 2. The external diameter is 90, while the length is 117.5. The internal diameter is 0. So what is going to happen here, just like we did initially, the G92, just to set the offset, because if you minus 22.5 from the 117.5 minus 22.5, that's 95. So The surface of the workpiece now is 95 after 22.5 must have been held by the choke of the headstock, which will be inaccessible to the tool. So G23 is just to move the tool to a convenient space. M21 is to close the door. Then G00, start the spindle. Spindle start clockwise. M08, like we discussed, absolute. Then G94 to feed rate per minute mode. Then G96 here is to have a constant surface speed with a spindle speed of 200. So the embedded 222. So let's see, it's a drill of 20 mm diameter, and the diameter of the drill itself is equally 20 mm. So what will happen here is that the tool will be changed to the drill of 20 mm drill, so that an internal diameter of 20 mm can be created in the workpiece. G01 is linear interpolation, so the coordinate is x0, z5 away from top of the workpiece. The feed rate is 90, so F is the feed rate. Now G74 is a peg drilling. Now, because in machining operations, when you are creating a hole into a workpiece using the drill, it becomes very hot, so, and which can damage the drill itself. So that the drill can cool down each time it goes into the workpiece is what the peg drilling does. So the first block of the G74 is that the tool should be retracted 2 mm each time the drill goes into the workpiece. It should come out again by 2 mm. It should retract by 2 mm before it takes another cut, retract again by 2 mm. So that is the first block of the G74 here. And the second block here is the depth of cut, which is Z minus 40, so that the drill will go in by Z by minus 40. The length of the hole that we created by 20 mm drill will be 40 mm length, while the K number here is the depth of cut for each peck. So K5, which means for every peck 5 mm will be drilled, and it will withdraw by 2 mm, drill another 5 mm, withdraw by 2 mm, drill another 5 mm until the length of 40 is attained. Now G28 again is to move the tool to a convenient position. So to change to T1, we already discussed G71 over time, so I believe you understand that by now. Then there's another tool change here, which is T9. Let's look at T9. What tool is on? So T9 here is a 4 mm grooving tool. So we want to create a groove on the workpiece, and we are taking a 4 mm grooving tool. So the groove is 4 mm, so that's why we're taking a 4 mm grooving tool. There are other grooving tool, 3 mm grooving tool. There's the 6 mm grooving tool as well. So whichever one is applicable to the work, but in this case we are taking a 4 mm grooving tool. So the T9 is the 4 mm grooving tool. The T9 is the 4 mm grooving tool, and the tool change command is the M08. So G00 is to move the tool to this coordinate without cutting, X72 Z minus 5. So because we are grooving on the profile of the workpiece, the tool will be on the workpiece. So that's why the Z coordinate in this case is negative, so that it can be at the starting point of the groove. So the grooving cycle is the G75, and G75 has two blocks. The first block is G75 R1. R is for tool retract, so tool retract by 1 mm each time the groove is created. The tool will come out by 1 mm. Now the second block of the G75 count cycle has the coordinate, that is the X, the Z, the P number, the Q number, and the feed rate. Now the X here is the diameter in the groove. So the workpiece diameter itself has been reduced to
from here it has been reduced to 70. So 70 here in this roughing count cycle. So the groove will take it down to 50, and the length of the groove on the workpiece is 40, and the groove is starting on a length of 5 and is ending on a length of 40 on the workpiece. The P and the Q number are in 1000, so this P5000 will be 5 mm, so which means the groove will be 5 mm, while the Q number, which is this Q10000, will be Q10. That means the distance between each groove, that's the stepping distance between each groove will be 10 mm, and the feed rate is just F30, so the feed rate here is 30. Likewise, you have a feed rate of 50 here and a feed rate of 90 here. So each time you are using any count cycle, the feed rate has to be specified in that count cycle. So I haven't specified all these numbers. The next thing is just to run the program. Let me just go over the G75 again. The second block of the G75, the X, the Z, the P, the Q, the F. The X is the diameter, the finishing diameter on X-axis in each of the groove. The Z-40 is the length that the groove will cover on the workpiece. The P number and the Q number are in 1000. So this P5000 is divided by 1000, so that will be P5. That will be 5 mm. So which means the grooving is done in 55 mm. The cutting is taken in 55 mm. While the Q10000 divided by 1000, that will be Q10. The distance between each groove will be 10 mm. While the feed rate is 30 meters per second. So let's just run the code and see how. So the workpiece has been added, the tool has been changed, the door is being closed now. So the tool has been changed to a drill. So here is where the peg drilling will be done. You can see the movement of the drill inward and outward. So that has been created. It has created the hole. So the next thing is to change the tool again. The tool has been changed to the external roughing tool, so which is taking the step turn again to 70 mm. So this tool has been changed again. So that is the grooving now. The grooving is being done in a step of 10. So this distance is 10 mm and it's cutting 5 mm each cut, retracting by 2. So here is the finished profile. So here is the finished profile. We can see the groove. So this distance between each groove is 10 mm. That is what is being specified by the Q. So 10,000 divided by 1000, so that's 10 mm. The P number is the depth of cut into the groove, which is 5000 divided by 1000, that's 5 mm. And also the Z minus 40, so that means from this datum, which is the origin of the coordinates, to this point where we have the last groove here, is 40 mm. That's the length of the groove. Now the 50x50 here on this second block is the diameter of the groove, so that's 50 mm. This surface is 70 from this finishing and roughing cycle here, 70 on the surface, while the grooving diameter is 50. So let's just run the program again to have another look. So the workpiece has been added again. So the grooving is being done now. Let's see. Zoom it in. So that is the finished profile again. Okay, so for the milling operation, we have to change the machine tool to milling machine. So from here we can just do that. Check the milling machine. We are taking the milling center. Click open. Now, because we are working with CNC machine, like we already said, the MCU is an onboard PC, which is this box here in this case. And if you look at the table here, you clearly see this cross here, which indicates that this point is the origin of the milling machine. So this is where the X, Y, and Z axis are set at 0 by default on this milling machine. So here is where your tool would be, and the spindle and the chalk are equally here, just as you would have in your real life CNC milling machine. So if you go to the inventory browser of your CNC Simulator Pro and you go to embedded milling tools, so there are 68 milling tools with the description equally specified here. So tool number 1 is end mill millimeter. The diameter is 6 mm and the tool length is 50 mm. And also for other kind of tools that are available, the drill 8 mm diameter, the tip angle 120 mm, the tool length, depending on the profile that is to be obtained on the workpiece, will determine which tool should be used. So for the milling workpieces, so for the milling workpieces, there are 3 parts which I have created here: part 1, part 2, and part 3. And you can create a part also for yourself. So we can try to add a part. Let me say there's a new part is to be added, which is part number 4. So you'll be required to put in the size in x-axis. So what's the size? Because the milling machine is a 3D machine. It has 3 coordinates: the x, the y, and the z. Unlike the lathe that has only the x and the z axis. So yes, here you have to specify the length of the material in x axis. Let me say I'm putting here, maybe I'm putting here 200 for x axis, and I'm putting here 130 for y axis, and I'm putting 5 mm for the z axis. That means the thickness of the workpiece is 5 mm, depending on whatever workpiece dimension that you want to work with. So to work with this milling machine, the first thing is to put the workpiece on the table. Then with the appropriate tool, with the profile diagram, the part program can be written and the profile will be obtained. So the first profile that we'll be looking at here is this profile. Now the question requires us to write the manual part program to mill out this profile on this workpiece, and the depth of the profile this profile here is 10 mm. So since the profile is to be done to a depth of 10 mm, which implies that the same program that generates this profile one time can be repeated 10 times, because it's not possible to be taking a depth of cut of 10 mm to be milling out 10 mm from the workpiece. You don't want to damage the tool, so you can be taking it 1 mm each time. So the same program that will go for 1 mm throughout this profile, when repeated 10 times, we generate this profile with a depth of 10 mm. And here we have dimension of the workpiece itself. From here to here, that's 20 in 5 places, that's 100. Also here we have 20, 30, 30, 20, which call it 100. So the X and Y axis is 100 by 100. And since the depth is 10 mm depth, definitely the workpiece dimension in Z-axis must be more than 10 mm. So the rough stock here, so the part for this profile, the rough stock, is part number 1 for the milling. We can just look at that. The dimension is X100, Y100 and Z10. So the mill workpieces for part 1 with a dimension of X100, Y100 and Z10. So here is the, so this is part 1 with a dimension of X100, Y100 and Z10. So this first line is the main program. Now, why this program is written in main and sub program? Because you notice there's a sub program here and there's a main program here. Now, because the profile is to be done to a depth of 10 mm, like I already said, and one cannot take out 10 mm in a single cut. So you can be doing it probably 1 mm or 2 mm or 3 mm. But in this case, I want to do it in 1 mm, so that will be done 10 times to get a depth of 10 mm. So with the main program, what I want to do is to position my tool, and with the sub program is where the 1 mm cut will be repeated 10 times. So let me just run through the lines so that we'll get to understand it. Now, this O alphabet and the 4 numerical digits here only specifies the program number in this case. So I'm giving the main program 01001. So that's the main program. So the next thing is to add the part. So by adding the part will be on the table, and the part 1, which is the part to be added in this case, which is the rough stock for this work, is of the dimension X100, Y100, Z100. Now, when part is to be added on the milling CNC machine, one needs to specify the X and Y coordinates that the parts will be placed on the table. And here I'm specifying X40, Y30. So the workpiece will be placed on this table at a coordinate of X40 and Y30. Why that is important is because at the time I want to set my 0 offset, the same way we did for the lathe, when I want to transfer this crosshair to the origin, where I want my origin to be on my workpiece, I will need this point to locate the origin. So G92 is the 0 offset, and I'm putting the 0 offset. Now I want to move this cursor from here to the workpiece. So I'm setting it at X40, Y30 and Z10. So which means the corner of the workpiece will be the origin now with this G92. So G90 absolute, G21 the dimensions are in mm, and G95 is the feed rate, the feed revolution per revolution mode. Now the first thing is to put the appropriate tool. So the tool I want to use is the embedded tool number 2. So if we go back and look at what that tool looks like for embedded milling tools, tool number 2 is an end mill with a diameter of 8 in this case. So, and because the tool has its own diameter, and we talked about quarter compensation because you don't want the radius of the tool to be cut into your profile. So I'm putting in the quarter compensation in this case. So that's G42 D8. So the D number is the diameter of the tool, which you have seen to be 8 mm. So S1000, that's the spindle speed 1000. M03 is for the spindle to start clockwise, and M08 is for the coolant to be turned on. So G00 is just for rapid transverse without cutting. So, and I want the tool to be away from the workpiece. So the tool will go to X minus 10, Y minus 10, and Z5. So the tool will go away from the origin in the negative direction, and it will go above the workpiece, because for the milling, the surface of the workpiece have been set to be Z0 from this line with G92. So anything away from the workpiece is positive, anything into the workpiece on the Z-axis is negative. So Z minus 5 will be into the workpiece and Z5 will be away from the workpiece. So after my tool has been set to the home position with this line, then I want to start my sub program. So at this point is where I want to call the sub program. So for the sub program here, M98 is the core sub program, and M99 is the return from the subroutine or the sub program, as in you want to close your sub program. M99 to call a sub program is M98. So for calling a sub program, the alphabet P has a series of numbers. Now alphabet P and the first three numbers after the alphabet P is the number of time that subprogram would be called. So in this case, P005 means that the subprogram will be called 5 times in this case. Now the other 4 numbers, which is 9001, is the program number for the subprogram. So the P number here, the first 3 alphabets, is the number of times that subprogram will be called, and the following 4 alphabets, the following 4 digits is the subprogram number. So 09001 is now the subprogram number, which will be called 5 times with this M98 here. So what will be done within that subprogram? G01, which is linear interpolation. Now if you look at this profile, we'll see that at this point here is X20 Y20. This point is X20 Y20, and if the cutter is going in this direction, so this will be X40 and Y20. And we're already told that the radius of this arc is 10. And also the radius of this arc here is 30. So to move from here to here, we'll see that this is a clockwise motion. So that will be a G02 to move from X40 to X60 with a radius of 10 will be a G02 because it's a clockwise motion. So at this point again, we have to return to linear interpolation because from this coordinate to this coordinate, the straight line profile. So from X60 to X80, the same Y20 because we are still on the same coordinate on Y. It's a linear interpolation, so that will be G01 X80 X80. So it goes up from X80 to Y50 because if we calculate from here to this point, this is Y50. So from Y50 all the way here to X20. So X at this point is X80 Y50, while at the end of this arc here is X20 Y50. So to move in this direction is a counterclockwise interpolation. So that is a G03. So at this point, so that will be G03 X20 Y50. So Y50 with the radius of 30. So this arc will be created to this point, and from then on you have to change back to linear interpolation because to move from this coordinate here X20 Y50 back to X20 Y20 down here, it's a linear interpolation. So that will be G01 X20 Y20. So that is what will be done for 5 times in this sub program. So G01 X20 Y20 Z5, and the feed rate is 90. So you will notice at any point you are putting in a G01 for the first time, the feed rate has to be specified, else no cutting will take place. So that's why the feed rate is here. So Z minus 1, so the Z axis, the cutter will go into the workpiece at this point of X20 Y20 with a depth of minus 1 mm. So 1 mm will be cut into the workpiece. So the next coordinate of X is X60 because that's a linear interpolation. X60, then anti-clockwise interpolation with G03 to X80 Y40 with a radius of 20. G01 again, linear interpolation to Y60, and clockwise interpolation X20 X60 Y80, linear interpolation again to X40, then G03, that's counterclockwise interpolation X20 Y60, then R20, radius of 20, then G01 Y20. So to stop the subroutine is M99, and the cutter compensation cancel is G40. So G00 without cutting, Z5 away from the workpiece, the tool will go away from the workpiece. Then G28 is just to take the tool to a convenient position away from the workpiece. M05 is to put the spindle off or stop the spindle. M09 stop the coolant, and M02 is to stop the program, the end of the program. So let's just run this and see. So the workpiece has been added, and we can see that the cursor has been moved to this point. So we can see now. So that is doing that 5 times. So we can see, okay, so the profile is this is the profile that we have done, not the one I showed initially. So this is the profile that is required, and the depth is 5 mm. So this is the dimension, 100 by 100, and this is the profile. So these are the coordinates of x and y, and the radius of 20, another radius of 20 here. So this is the profile. We can also run it again just to see. We can see that the point here has been taken as the origin. So the cutter moves into the workpiece and takes the first 1 mm cut. So it does that 5 times because we have P005. So this subroutine will be done 5 times. That's the profile. So let's look at the code for this. So this is the part program for this profile. So the dimension of the workpiece is 100 by 100, and the thickness is equally 10 mm. So that is what is being done here, and the points, the coordinate at which the workpiece is added on the table is 40 on x-axis and 30 on y-axis. So G92 is being used to set the origin on the workpiece, x40, y30, z10 to be the new origin, G90 absolute, G21, G95 for the feed revolution mode. So embedded to 1 M06, that's the tool in the 2 chamber 1. This is the spindle speed. This is clockwise spindle direction and coolant on. So also the G00 is to set the tool to its own position. The home position in this case is x minus 10, y minus 10, and z5. So it's away from the surface of the workpiece, and the tool is being brought back to x20, y20. So the tool will now be brought to this point, x20, y20, because we look at it, this is x20 and this is y20 at this point. So but z5 is still away from the workpiece. So G00, Z0, so just at the surface of the workpiece, the feed rate of 35. Because we are using the G01 for the first time, we need to put the feed rate there. Now this is the sub program, because we are requested to make the profile to a depth of 10 mm. So, and from this program here, we are taking 1 mm per cycle, per pass. So the number of passes that we're going to have now will be 10 passes. So this is the program number for the main program, O2003. It's just a 4 digit of any number that you are comfortable with, but the O indicates that it is the program number. So this is for the main program, and this O9000 is the sub program. So the M98 is the sub program call, and the P number has a series of digits that has to be understood. Now the first 3 digits is the number of times the subprogram would be called. In this case, P010. So that means the subprogram will be called 10 times, because we are requested to make the profile to a depth of 10 mm, and for each pass we are taking 1 mm. So the subprogram will be called 10 times to get our profile to 10 mm. Then the next 4 digits is the subroutine or subprogram number, which is this 9000 here. So this is the subprogram that will be called 10 times with this M98. So G92 in the subprogram, the origin has been set. We are just repeating that here. G90, just the same thing. Now G01 Z-1 F35. So that's the feed rate in the subprogram. So Z-1. So it's going to take away 1 mm at this point at the origin of X40 Y30. So then G02 G01 X40 Y20. So X40 Y20. So to move X40 to this point, Y20. So this is clockwise motion with a radius of 10. That is circular interpolation. That's G02 from X40 to X60 Y20 R10. So that is what is happening here. X60 Y20 R10. So that is this arc here. X60 20 Y20 R10 with the G02, that is clockwise. Then G01 X80 Y20 X80 here Y20 G01, because this is a linear interpolation from this coordinate to this coordinate. The next thing is to go upward with Y50, then counterclockwise interpolation, that's G03 R30 Y50 X20 to this point, then linear interpolation back to this point. That will be X20 Y20 G01 X20 Y20, which is this line here. So this is the G03 R30. So after that, the subprogram is closed with M99. So everything within here will be called 10 times with this P010. So here is just to take the tool away from the workpiece and set the tool at this coordinate. G28 is to take the tool to a very far coordinate away from the workpiece. M05 to put the window off, plant of M08, then M02 to stop the end of the program. So let's just run this and see the profile. You can see here. So this is what has been done. That will be done 10 times. So the profile has been done. So let's say, for instance, I want to drill a hole just at the center of this workpiece here, at the center of this profile here, sorry. So after the sub program, I can just come down here and look at the tool, the drill tool that I'm going to use. Go to embedded milling. So let's look at what tool is a drill in this to registry. So this is a drill, so that's E18. So let me say I want to create this 12 mm hole just at the center of this profile. So I need to change the tool to this drill, which is a diameter of 12. So E18. After the tool has gone to a very far place, so E18, ET18. So you can see that's a drill. See here, that's a drill. E18 M06. So that's the 2-chain command. M06. M06. So the next thing is to bring the tool to the coordinate that I want to drill. So let me say it's coming at this center. So that will be X50, Y50. So G00, X50, Y50, Z5. So to stay away from the surface of the workpiece. So next thing I want to bring it inward. So that will be G01, Z minus 5. So the drill will go in with a depth of 5 mm. So after that, I just want to take the tool away from the workpiece. Let me just copy this line, put it here. So to Z minus 5 with G00 and to the coordinate of X minus 10, Y minus 10, and after G28, and M05 and all of that. So let me just run this. So let's see how that would work. So after the profile has been created, a hole will be drilled at the center of this profile. So this profile would be a depth of 10. That's why this sub-program here is called 10 times with the P010. So it's looping within this sub-program. So the tool has been changed to the drill, you can see. So look at it now. We have the hole in between the profile. So that's the hole that has been created with the drill. So the depth can be further increased if we so desire. That is the sub program and profile creation using the milling CNC machine. So with that, we'll be closing this session of CNC machine course. So if you have any question, you can send them to the link below for further discussions or clarifications on this course or some other related issues with CNC operations. So thank you very much for your time.